And so the afternoon session, the last session of the meeting, we'll have two presentations, one by Art Nozick and one by Howard Schmidt. The first one, Art, let's get you up here. And we're going to microphone him. Lapel mic? Art's from NREL, actually SERI as I remember it, but I guess it's really NREL right now. And he'll talk to us about quantum dots and kind of the next generation. This is actually 3+ generation of next solar photovoltaics.
Okay, thank you very much, and also thank you to the organizers. In this talk, I'd like to discuss our work at NREL, which actually I've been involved in since I've joined NREL over 25 years ago. But I'm happy to report that I'll be presenting what I consider to be a breakthrough, at least in the scientific aspect of this research. Whether it can be implemented in real devices and produce the high efficiency that we've been looking for remains to be seen. But I'll be talking about this third generation approach to solar photon conversion, which includes production of electricity and fuels. That's covered by the term solar photon conversion rather than photovoltaics. And in particular talk about the possibility for ultra-high efficiency using nanocrystals, also called quantum dots, where one can generate more than one carrier or electron hole pair per photon. Just briefly like to thank the people involved in the work. It includes staff, Randy Ellingson and Olga Mishish, and some graduate students who work with me through the University of Colorado, Ping Rong Yu and Jeff Blackburn and Jim Murphy. And a very important collaborator is Sasha Efros, who's one of the earliest theorists who developed the models for quantization effects in semiconductors in the early 80s when he was in Leningrad. Now he's at the Naval Research Lab. So, pardon me? Oh. Okay, first, well, you've seen these slides, but the first part is of the talk is to rationalize why it's important, at least in my view and people that work with me, to develop ultra-high efficiency. And this is the plot taken from Hoffert's Nature article showing that, we need something like 10 to 20 terawatts if we want to stabilize CO2 at 550 parts per million in 2050. And Nate showed this also, which I think is an important point, that first of all, the cost of photovoltaics, or the cost of electricity currently, say, 5 cents per kilowatt hour, but that's about 5 times the cost of conventional fossil fuel in the form of liquid fuel. And electricity globally only accounts for 25% of the utilization. So in order to make solar photon conversion make an impact, it also should address the other 3/4 of the energy required. And so the cost currently for photovoltaics is about 5 times that for fossil, and so this is where this number 10 to 50-fold decrease, which was proposed in the NRC report recently, you need to decrease the cost 10-fold if you want to just compete with electricity produced by fossil, but you have to go down by a factor of 50 if you want to produce fuel that would be competitive with current costs of fuel, and this is required in order to prevent economic disruption. I mean, if we want to maintain the standard of living globally, this is what these kinds of cost reductions are necessary in both electricity and fuel. In terms of photovoltaics, one can define 3 three types of regimes. This was defined by Martin Green, an Australian who is at the University of New South Wales. So the first generation is already here. The second generation you heard about from Ken's talk on thin film materials, and we include in there the dye-sensitized solar cell. Now, by third generation, we mean generally those systems which can exceed the thermodynamic limit first proposed and calculated by Cuissard and Shockley maybe 40 years ago. And I list some of the possible approaches to this third generation. Now, I include a regime, and it doesn't quite fit the second or the third. Well, it fits the third, but it's not third generation because it's here already, whereas third generation is more considered to be future approaches, and that's the multi-band gap tandem solar cell, which can have efficiencies higher than 31%. That's why I put it in italics. But the others include hot electron converters, which I'll talk about, the quantum dot solar cells, the impact ionization, and exciton multiplication. And there's some other approaches which I won't talk about. Other people are working on those, like the mid-band photovoltaics and moderating the nature of the light before it is absorbed in the solar cell by photon up conversion or down conversion. Now, just a little bit about the economics. This has to do with why I believe we need the ultra-high efficiency. Ken Zweibel had this plot, so you can calculate the dollars per peak watt as a combination of module cost, efficiency, and balance of system costs, plus some constant factor related to the power conditioning. And $1 per peak watts can translate that to approximately 5 cents per kilowatt hour. Now, in order for solar photon conversion to produce both fuel and electricity economically at 1 to 2 cents per kilowatt hour to make it have the major impact, this would require a conversion system at about 40 cents per peak watt, based on these numbers. Now, again, this comes from Martin Green, and it shows the three regimes of photovoltaic conversion. And these dashed lines represent a given dollar per peak watt. So any combination of aerial cost, dollars per square meter, and efficiency, just multiply this by a kilowatt per square meter, puts you, and if you're on that line, that'll give you this given cost per peak watt. Now, the point I'd like to make is that, well, there's a lot of effort on reducing the cost, but this is not enough, because if you do want to get to 1 to 2 cents per kilowatt hour, you can show that, using that equation up here, that if you could reduce it to $75 for the balance of systems, it's currently this number, and if you reduce the module to $50, which is, it's this number, so these are major reductions in cost, you would need the module efficiency to be about 40% and the cell efficiency, since you lose some in the module, say about 50%. Now, Ken indicated they could do this with thin film materials that are already being studied. So, they're talking about $30 per, it's consistent. They can produce their system at $30 per square meter. It's correct that, let's see, does this go backwards? Yeah. So if they're $30 per square meter, then, and they're at 10%, they'd be on a line here. Yeah, they could do it. But this is the first time I've heard that they could actually get it that low. The number that I'd use for the minimum, if you had a free solar converter, the balance of system costs would be at least $80, and maybe, that's a bad assumption. But if that were correct, and you wanted to be on a line like this to get 40 cents per kilowatt hour, at a reasonable, at this just with the balance of system, with a free converter, you'd have to have an efficiency greater than the Shockley-Quisar limit. So this was the driving force for our interest in producing high efficiency along with low cost, moderately low cost, not as low as $30 per square meter, but somewhere in here, maybe $100 a square meter. So that's the rationale for it. And how do we achieve it? Well, first, just looking at what limits the efficiency. The major limitation is the fact that for a single bandgap absorber optimized at 1 to 1.4 EV, the solar photons ranging from 3.5 in the near ultraviolet to half of EV out in the near infrared results in a energy loss of the high energy photons absorbed, say, in an optimum bandgap converter. And in the Shockley-Quisar analysis, it was assumed that this extra energy, which is in the form of kinetic energy of the electrons and holes, is converted into heat. So when you do the thermodynamics, you want to look for the conversion of the free energy of the photon into the free energy of the electricity or the chemical fuel. This is a loss, and that's how you come up with the 31%. Now, this has been a good assumption until recently because this process is very fast in bulk semiconductors. It occurs in a sub-picosecond time scale, 10 to the minus, probably 10 to the minus 13 seconds. And so that's how you get the 32%. You assume all the electrons and photons equilibrate very rapidly, and you can't utilize that extra energy. Now, over 20 years ago, we showed that, well, if you could use those carriers at the energy at which they were created, you could more than double the efficiency. This is the electron temperature. You could assign a temperature to the electrons if they equilibrate with each other. And it's the same value that you would get if you had an infinite stack of band gaps matched to the solar spectrum. Thermodynamically, you have the same final state. And just a minute, or just before I get into discussing that further, I just want to indicate that, as I said, this applies not only to production of solar electricity, but to solar fuels through the process of either photolytic water splitting or artificial photosynthesis, taking CO2 and water to make fuels and chemicals directly, as opposed to going around this cycle here. And I don't know, people may not realize that all the important but simple reactions like water splitting and reduction of CO2 to methanol or methane or even nitrogen reduction are all fairly equivalent in energetics and can be driven with sunlight. So it's a question of the thermodynamics is there. There's enough free energy in the photons to drive these uphill reactions. The question of the path, finding a catalyst, if you will. And Nate talked about water splitting. This is, as he said, this was studied intently in the 70s. Nate was involved. I was involved. Many people studied photolytic water splitting and gave up because the semiconductors didn't have enough stability if they had a low band gap to absorb enough light, and they didn't absorb enough light if they had good stability. And then recently there's the Gretzel cell, dye-sensitized cell. I'll mention this because one configuration that we can use the quantum dots in with the carrier multiplication is in a Gretzel-type cell where we would substitute quantum dots for the dye. So these are, again, the various ways to get above the Shockley-Quisar limit, and I'll only concentrate on this second category. The other ones I think you know about, or you can read the literature. There's a couple of books that these two books discuss these other approaches, one by Martin Green and one by Antonio Luca. Now, there are two ways to utilize the hot electrons. We for many years we tried to extract them before they thermalize. This is a tough business because in bulk materials, they thermalize in the sub-picosecond time scale. And so this is a very difficult process. We had very limited success. But recently, we realized that you could generate additional carriers if the photon energy was sufficiently high. And this, in bulk materials, this is known. It's called impact ionization. It's been observed previously in silicon and germanium and other semiconductors. But, and the thermodynamics has been looked at by many people, most recently by Landsberg about 3 years ago. And the efficiency, as you would expect, is close to what we calculate for conversion of hot electrons in general. Now, this process does require some specific balancing of rates because you want this energetic electron to undergo, we'll call it impact ionization. We actually have to change the term now in quantum dots because the process we have discovered is different. But in bulk materials, this electron scatters off of another electron in the valence band and creates a second electron. So you get 2 electrons per photon. But that process has to compete with the cooling, which I said is very fast, has to complete with electron transfer. That's not a problem. That's slower usually than cooling. And it has to compete with the inverse processes where you have 2 electrons, one of which will combine with the whole and to give its energy to the remaining electron and excite it. So that's the inverse of this, or this is called forward Auger, and this is the inverse Auger. Now, this process was examined for bulk semiconductors, but in addition to balancing energy, you have to balance momentum. And because of that, you can't drive the multiplication with just a band gap photon. And you have to have the change in the momentum of the electron balance that for the photon. So you need a much higher energy. And therefore, in addition to that, the rate of impact ionization requires, say, for silicon, going to about 5 times the band gap. So between the two, it turns out that impact ionization, say, for silicon, doesn't even begin to show up until you're 4 to 5 times the band gap out here in the ultraviolet. And even then, you only get maybe 20% increase in quantum yield. So it's for bulk semiconductors to use this for PV. It's not important. And this is where size quantization comes in, because we find that the system is totally, or the situation is totally changed now when you go to the quantized regime, which is when you squeeze the electrons and holes into a space that's very small, in the order of the Bohr radius of the electron hole excitonic radius. And as you know, you can confine the electrons in 1 dimension, quantum wells, 2-dimension, quantum wires, or 3-dimension quantum dots or nanocrystals. And this changes the density of states and makes the material look more like an atom than the bulk material, which has a continuous density of states. This will have discrete levels. Now, there's, quantum dots and nanocrystals is a huge field now. There's a tremendous amount of work going on, and it shows very interesting properties. For instance, you've all seen this probably. You can change the emission and absorption characteristics by just changing the size of the quantum dot as opposed to changing the material. But the things that we want to concentrate on, the effects of quantization, include slowing down the cooling, the electron phonon emission, and enhancing this, what we thought was going to be impact ionization. So some of these slides still call it impact ionization, but at quantum dots, it's not really impact ionization. But it's the inverse of the Auger, which is creating 1 high-energy carrier from 2 low-energy carriers. And one of the reasons why the relaxation is slower in a quantum dot is that because you have discrete states and you want to go from one level to the next, because of the small size, these levels can be separated by several hundred MeV, which is 5-6 times the phonon energy. So you need many phonons in order to go from, say, n equals 3 to n equals 2. So that's called the phonon bottleneck. And so the idea is that you're going to slow down the cooling because of the quantization. That'll allow a more probability for doing this carrier multiplication. And there's some history as to how I came upon this idea. It has to do with the blinking that occurs in single quantum dots when you look at the PL from a single dot, which the explanation was developed by Efros and had to do with the ionization, the Auger ionization, because when this process occurs, this electron being out here produces a charge in the core which quenches the luminescence, and when it comes back, it turns it back on. That's the explanation for blinking. So it became apparent to me, well, if you could do this, you should do the inverse, which is to have a high-energy photon create 2 electron-hole pairs. And we were looking for this for many years. We started about 1981 or so. But we were looking at materials where this process was difficult to see, and we were scooped in May by Victor Klimov at Los Alamos, who found this to be very efficient in lead selenide. We were looking at the 3,5s, indium arsenide, indium phosphide, and other 3,5 low band gap semiconductors, indium arsenide. So we jumped to lead selenide after. I actually got this to review in February, so I got a couple months jump on this. So we jumped into lead selenide, and we found some very interesting properties which went beyond what was published by Klimov, in particular the model for this. So what's important here is to do the time-resolved dynamics, which is done by luminescence or transient absorption. I'll just run through this. This is just the theoretical energy levels as a function of 1 over the size of the squared of the quantum dot, showing this fan-like structure due to the quantization. Our experimental absorption data, match this theoretical thing pretty well. The critical data is this looking at the decay of the longer time decay of the carriers once they're created as a function of the photon energy. And it's expressed as the ratio of the photon energy to the band gap. So as we go from 1.9 to 5, we get this increase in the. This is a bleat. This is a photo-induced absorption in the mid-infrared, and we see growing in a fast component. And this is the signature of a biexciton or a triexciton, because the lifetime of a biexciton is much faster than a single exciton by orders of magnitude. The decay here is maybe 40 picoseconds. For a biexciton or a triexciton, it's about 20 picoseconds. And for a single exciton, it's nanoseconds. And we go through analysis based on the magnitude of the bleach, because that determines that's proportional to the population, and the time scale of the decay. And we can generate quantum yields, and this is the really the most important slide, because it shows the quantum yield in percent as a function of the photon energy. And we've done many, many experiments just to get good statistics. And what you see here is, and this is the size of the quantum dot. I don't have the dimension, but this is 5.4 nanometers to 3.7, 3.7 nanometers to 5.4. And this is the HOMO-LUMO, the band gap, effective band gap of the quantum dot. And you see for the smallest band gap at around 3 times the HOMO-LUMO transition, which corresponds to about 2.7 eV, so it's still in the visible, we begin to get a very dramatic rise in the quantum yield. And when we're at 4 times the band gap, we're getting 3 electrons per photon. So this is quite remarkable to get a quantum yield of 300%. Now, the other important thing, as I mentioned, is that the explanation for this is based on a new paradigm for this effect. It's not impact ionization. It's actually a quantum mechanical effect. It's related to the Schrödinger cat, where if you have equivalent states, you can show that the real world consists of a superposition of these states. So energetically, this is the band gap, and we can show that the transition from 2p to 2p of this should be a hole, 2p of the hole level to 2p of the electron is equivalent to having 3 excitons at the 1s levels, or also a bi-exciton, one of which has an excited hole or an excited electron. So you have this produced instantly, and then you will have oscillations or quantum beats between these states. And so we did the time-resolved transient absorption to look for this. And first, it just shows exciting at the band edge. You just get the fast rise due to the instrument-limited response because you create the electron in hole right at the 1s, or the homo-lumo, so you'll see the full bleach immediately. But then when you go to 2 and 3 and 4, you begin to see this slower component, which does show some oscillation, and this is reproducible, and it can be fit by the theory. This was done by Efros. This shows the oscillation that's produced by the quantum beats at twice the band gap, and this shows the oscillation, which is deeper, at 3 times the band gap. This just shows, in the case of 3 times the band gap, you have 4 equivalent states that they oscillate, and what determines how many excitons you're left with is the dephasing, which of these states undergoes dephasing through phonon interaction. This state, having an asymmetric charge distribution in the dot, it will have a stronger coupling with the phonons. So during this oscillation, this one is, this state, let's see, the one with, I don't show the 3 electrons, but the state that has 2 bi-exciton will undergo the dephasing, and you wind up with 2. It's possible to also generate 3, which you need to go to 4 times the band gap. I didn't show it. It gets complicated because you have many more states that can be superimposed. We just begun to look at how to utilize, what effect will this have in a cell. As I say, we're going to ultimately try to develop this for Grätzel cells and other devices, which I'll briefly show. But you can make a calculation of the improvement in the efficiency depending on the absorption characteristics. In the best case, you would have, for each band gap, you'd have another electron hole pair generated. So you'd have a staircase here up to, 7 or 8 electrons per photon at high enough energies. And Mark Hanna was doing these simulations, and so he showed that what you could get an improved efficiency if this is with no carrier multiplication. You just get the normal 30% efficiency. With the experimental data shown in green, it's not optimized because you'd want the band gap to be about 0.5. The bulk band gap of lead selenide is 0.28 EV, but there is there's some improvement here. And then in the ideal case, where you had that stepwise function, you could get up to about 40% efficiency. This is less than the 60% calculated thermodynamically because it includes real life values of surface recombination and other factors that are not thermodynamically limited. Oops. Okay, I think I'll conclude here. I just would mention that there are 3 configurations I could conceive of, maybe there's more, that would utilize quantum dots with this carrier multiplication effect to improve the efficiency. One is just replacing the dye with these multiple exciton generating dots, and then you would get a higher photocurrent. We're going to model the effect in a Gretzel-type cell. The other cell would be just to disperse the dots in the hole in electron-conducting polymer and get charge separated. You could use other, hole and electron acceptors, but the general idea is the same. You would have a interdispersed polymer blend of hole and electron-conducting polymers with the quantum dots embedded, and if you get 3 electrons per photon, that should improve the efficiency. And the final configuration would be one where you have an all-solid-state device where you'd have a PIN structure with the I region consisting of an array of quantum dots like this, and you'd get coupling. You have to have 4 mini-bands between the dots and get transport, but again, you would come out ahead if you were able to get the efficient carrier multiplication. So I'll just finish with the conclusions. Size quantization can greatly affect the dynamics of relaxation of carriers. It slows down the cooling, and we've shown you can get very efficient exciton multiplication. And we've developed a new model. This work's just been sent into Science last week, so I hope it makes it there. It's a tough bar to jump over, but we think this is the first time it's been shown that a photon can instantly create more than 1 electron-hole pair. So this is the real novelty of the model. And so ultimately, we believe, I didn't talk about the electron transfer because you'd also have to get the proper electron transfer dynamics, but you can control that with the spacer between the dot and the semiconductor. But we believe that based on these results, we're optimistic that we can improve the efficiency of solar photon conversion using quantum dots. Thank you.
Thanks, Art. Thanks, Art. Any questions, Ken?
Let me first congratulate you on creating more than 1 exciton. That's really pretty wonderful. Just to clarify some of the possible confusion about costs and assumptions, in the calculations that I showed, I assumed a much lower balance of system cost. And I think that's consistent with both the long-term and perhaps a larger field application. Mm-hmm. I think we have to probably, to do everybody a favor, do some kind of timeline and application-specific assumptions about our BOS costs so we can integrate that back into these kinds of discussions. I don't think that really affects what you're doing because you're showing us a new horizon for improved efficiency, which is always welcome. I just think it affects what the different possibilities can do in terms of reaching low cost. And the low-cost challenge is still there because, as everybody knows, making fuels, et cetera, makes no sense if you don't have really ultra-low cost. So we need all the help we can get there. We also need to include the fact that if we go where the sun is, that we're going to get another advantage that we haven't really included in most PV cost calculations because we do them for average locations.
Mm-hmm. Yeah, I agree with what you said.
Other questions?
Any experimental calculation about temperature dependence or relaxation time?
What dependence?
Temperature dependence.
Oh, temperature.
Yeah.
There's not a very big temperature dependence.
So it's not changing.
Right. No, it doesn't have a strong dependence on temperature. Yeah.
So that was really great. I've got a question about the efficiencies that were calculated from that half a volt band gap. So, normally the voltage you get is a lot less than the band gap because of just microscopic reversibility. These J0s are always in there. Mm-hmm. And so a half a volt band gap probably should only give you a 1/10 of a volt open circuit just from just putting in any reasonable lifetime of anything. And if that were the case, you couldn't get 40% because you'd need 400 milliamps per centimeter squared at a 1/10 of a volt. So to get the 40%, at half seems pretty hard. And if you went to 1 volt to get half a volt open circuit voltage, you might get from 33 to 40 milliamps because now you're further blue before you get 2 band gaps. So what actually went in to get the 40% number out of that?
Well, the band gap isn't what's controlling the current, because
I know that.
if you have a half a volt band gap, you really have to absorb 1 or 1.5 volt photons.
Yeah, but the question is what's controlling
the
voltage?
The voltage would, if it's in the Gretzel cell, the voltage is determined just like it would for the die, in that you would have to have the say the valence band, match to your counter electrode, whatever.
But the assumption was for half a volt band gap, you would get half a volt open circuit voltage.
Oh, but that wasn't a Gretzel cell.
Doesn't matter.
That was just a normal PN or some kind of a solid state device. Yeah, for Gretzel cell, we actually need to, I might mention, there's a molecular analog to this, which is, and we just got funded to do this. It's called singlet fission, where a singlet can produce 2 triplets. So we would use these dyes, and we have where our collaborators at Joseph Mickle at the University of Colorado is on the project. So he's got some ideas on how to get efficient singlet fission. In that case, to solve this problem, we would use 2 dyes. One to absorb the normal, to do one exciton per photon, and the other to absorb the high energy part of the spectrum and get 2. So this would presumably get much higher efficiency in a Gretzel configuration, but that remains to be shown.
I think this is a beautiful job. Congratulations. I'm pretty sure the answer is nothing, but what would you think concentration of sunlight could do to this?
Well, the thermodynamic calculations, of course, show as you go to concentration, you go from the 86% limit for total utilization of hot electrons, either making a higher voltage or making a higher current. You increase that from 66 to 86% at full solar concentration. I mean, that's like 10,000 suns or something like that. But yeah, concentration definitely would help.
There we go.
Other questions? I have one. Remind me again of the size criticality here for the nanodots.
The size criticality depends. You need to have the creation of discrete states, so you have to definitely be in the quantum size regime. And that depends on the effective mass of the
And optimal size?
And the optimum size, at least for these materials, would be in the range of 3 to 6 nanometers.
Thank you. Further questions? If not, let's thank our speaker. Thanks, Art. Our next presentation is by Howard Schmidt. Howard's the executive director of the Carbon Nanotechnology Laboratory here at Rice University, and he'll talk to us about single wall nanotube quantum wires. Howard, let's get you wired up.
Good afternoon. Wade, thanks very much for the invitation to speak here. It's been a great conference. I've learned a great deal. I want to tell you a little bit about what we're doing in the Carbon Nanotechnology Laboratory, where I get to work with Rick Smalley and Bob Hauge. One of our primary goals here is to build the nanotube quantum wire. And let me see if I can find this out here. And just a word from the sponsors here. The Nanotechnology Laboratory's goal is to basically make Bucky tubes be all they can be. It was founded a little over a year ago. Rick brought me on as the executive director. And basically our goal here is to increase the scale of the program and fulfill many of the visions for nanotubes that Rick has. Almost a personal note here. Why SWNT? And also why have a laboratory just focused on carbon nanotubes? Well, it has a unique combination of physical properties that have a lot of great applications, including probably the strongest fibrous material possible. It has excellent thermal conductivity, about 50% higher than that of diamond along the axis of the nanotube. It has a unique and very broad chemistry of carbon, so basically your whole organic textbook is available for manipulating and processing the materials. It has the scale and perfection of DNA. The tubes themselves are around about a nanometer in diameter, so it gets very interesting quantized electronic effects. And they can be up to, most recently, 4 centimeters in length for one molecule. They also have really unique electrical properties. These are polymers, but unlike any other polymers, they're very good conductors of electricity. And certain types of them are best metallic conductors known. Others are the best semiconductors known. For instance, Michael Fuhrer recently observed carrier mobilities in these tubes that were about 30% higher than indium antimonide that came out about a year ago. It's really pretty phenomenal. And I'm going to talk a lot more in the next few slides about the metallic conductivity. So in my mind, I think of this as the ultimate engineering material. And what's being passed around there, since very few people have actually seen nanotubes, is a bottle of the raw nanotube product. As you can see, it's very light and fluffy material. As it comes out of the reactor, 1 gram fills about a liter. So it's pretty challenging to work with. So with all those great properties, what would you want to do with it? This is kind of a silly marketing slide I prepared for NASA to show a huge variety of applications. And plainly, we can't work on all of these at one time. But a lot of these are electrically oriented, like if you have a very high current density conductor, you could think about making motors and actuators. There are certain digital electronic applications that are being pursued by Nantero. The high surface area lends itself towards supercapacitors and super batteries. But I'm going to focus down here on power bus applications here, which could actually be quite applicable to primary power distribution, both on spacecraft and, as we'll see later, on Earth. So the main program that we're focusing on, or I focus on, is the SWNT quantum wire. As you see, there's lots of applications, but you need to focus in on one thing, and this is a great lightning rod type project because it involves many supporting process technologies that will advance nanotube technology kind of across the board from production to applications. And so what we want to end up with is basically a crystalline array of metallic nanotubes. It's kind of like this, where but unlike this picture, not all nanotubes would go from one end to the other, but they would be more modest in length, several microns in length. So we would make a crystalline array of reasonably short segments. We expect that the conductivity of this material could be as great as 10 times that of copper, certainly equal to or two times better than copper, and should be about 6 times less dense than copper itself. A lot of industrial conductors are made out of aluminum, so it's about half the density of aluminum. Should be not very strong material, and in AC applications where we know eddy currents transverse to the axis. And unlike all other metals, it has a very, very low thermal expansion, which would eliminate one of the main primary failure modes in grid applications. So in the conductive applications, the key benefits are lower I²R losses, low to no sag, lower mass, and higher power density. And in this area here, which would be the concomitant effects and benefits on SWNT production, would be we need to come up with type and class specific production methodology. We'd also, by what we call the SWNT amplifier process, we should end up with basically about 1,000 times pure material at a lot lower cost. Also involved are a number of sidewall functionalization chemistries, which, by the by, help the material become dispersible and usable in polymer systems. And there's a picture up here at the top, which I want to bring your attention to. So I'll tell you that the basic electrical conductivity of this material is quite good. There have been any number now of routine measurements on individual nanotubes to show that the conductivity of a metallic tube is about 2 to 2.5 times that of copper. You can readily demonstrate that you can push 25 microamps of current through any one of these nanotubes. If you normalize that to, say, a square centimeter of cross-section, it's about 1 billion amps per square centimeter, which is a pretty phenomenal number. Now, it's dissipative, and you're not going to actually push that much current routinely through these things, but it does show the unique ballistic conduction properties of these nanotubes. Now, since we're not going to have individual nanotubes that can go from here to Dallas or from somewhere on the equator, from Erectena to Houston, we have to make these out of short nanotubes. And so there's been calculations done here by Lou that indicate that the effective transmission coefficient across overlaps of nanotubes essentially is 1 if they overlap by more than about 100 nanometers. And since we can make tubes that are routinely several microns to multiple microns, we think that we can fulfill that condition and get a good bulk conductivity of in an ensemble of tubes. Now, not all tubes are created equal. In that flask I passed around, there's actually about 50 different types of nanotubes. It has to do with how the hexagonal arrangement of carbon is made up as it goes down the axis. Now, this is a fluorescence excitation spectrum, and I'm not really addressing any photovoltaic or photochemical applications here, but it kind of shows along the way that there is very, very good optical activity and absorption through the infrared and the visible here. And so one of our jobs is to pick out a particular type of tube here. It turns out these are all semiconductors, and the ones that we're interested in for this project are here in the valley, what we call the Valley of the Metals, where they don't fluoresce. This tube up here is what we call an armchair nanotube. It has to do with the structure of the carbon atoms there on the end. This turns out to have a conduction that's like that of a true metal here. It has pretty good carrier density. And here, these other ones are variously semi-metals, which have conductivity similar to that of graphite with a microgap, and the other ones are the direct bandgap semiconductors. So there are about 150 of these types of tubes known, ranging from 1 to 3 nanometers in diameter. And the process that we use now produces about 50 of these right now. And so the current technology we have for producing the nanotubes is relatively impure and relatively inefficient. So what we want to do is gain control over the N and the M. That'll open up a whole number of applications. The primary one here is the quantum wire. And so if you think about how to grow these things, now they're grown right now from a spontaneously nucleated nanometer size iron catalyst particle. And then after the cap forms, it's thought that then the tube starts growing, but it can pick any one of these stable configurations. Now, what we think the right approach here is to use a seed of an original nanotube, to use that as a template to grow more material, and thereby essentially grow from a nucleation and a predefined metal catalyst particle that you put on purpose. So this should end up with a very much more efficient process with fewer byproducts and high purity. So this is a schematic of how we approach this. We call this the SWNT seeded growth program, in which we would start out with short nanotubes using a cutting process. We can take multi-micron length tubes and cut them down to 50 to 100 nanometer type seeds. And I'm not going to go into that. Then we'll take a chemically defined catalyst particle and attach it here in solution. Now, the chemical that we're using these days is what we call FEMOC. It's kind of a nickname for a 114 metal atom cluster that self-assembles out of solution. It has 30 carbon atoms, the balance from our molybdenum atoms, bound together by oxygens and a few acetates and a phosphorus atom in the center. And so we found that, working with our colleagues at the CNL, Andy Barron, Jim Tour, and Ed Billups primarily, that we can take this molecule and attach it either in ethanol solution or in chloroform to the carboxylic acids that are native at the end of the nanotube, make an adduct. And then, let's see here, these can be then deposited on a surface, and here you can see in this AFM some nanotube segments with the catalysts attached. In separate experiments, we've shown that we can now reductively dock that, and in which process the ligands and the oxygens disappear, and you can start to etch back and get an intimate contact between the catalyst particle and the seed tube. So we've done, of those process steps, everything except growth. I think we're hot on the trail of doing that and hope to have that achievement in the near future. this should be, we hope this can be scaled up to a commercial process at large scale eventually, and this would be what that kind of process would look like industrially, where you have a standard growth chamber where you're using seeds instead of promiscuously letting the seeds generate themselves. And say you're putting out 1,000 pounds a day, you then take about a pound out, and then do that cutting process, add the catalyst, and put it back into the reactor. And so we think that we can get gains in here on the order of 1,000, perhaps more, perhaps a bit less. But this is what we call the SWNT amplifier. The other major part of making a quantum wire from these, after we are able to produce, for instance, pure 1010 metallic tube production, is to assemble or crystallize those tubes into continuous fibers. And we've got to start on this using a process which was discovered here about 3 years ago, by which nanotubes will almost dissolve. They will disperse in concentrated acids, superacids, primarily oleum. And so what we can do, and this by a process is very similar to how Kevlar and Xylon are made. You can disperse the nanotubes in the oleum and then spin it out as a thick gel, shown here, through a long, narrow orifice, and take up to 100 meters at a time at this point. You'll end up with a nice fiber, and has some residual microstructure that is limiting its both its mechanical and its electrical properties at the time being. This is nowhere near where we want it to be, or where we think it can be. These are running about 1% of the conductivity of copper, about 1% of the strength, 1 to 10% of the strength that we expect. But we are routinely producing fibers that are, say, 50 microns in diameter. These have a cross-section of approximately 1 billion tubes. And so we're currently focusing on the connectivity of the subdomains and improving the crystallization properties of the material. So assuming we're successful in this, we can look ahead to, let's think some about what this would mean on the grid. Here's a slide that I borrowed from Wade, this doctored slide showing the blackout from last summer. So if we're able to make this material, and this is some calculations of how I think it might perform, should eliminate the thermal failures that cause this, which was caused by sagging into trees. And so there are a couple of key applications. One is in reducing the power dissipation in long-haul transport. And another one is to improve the amount of power you can actually get through high-density urban corridors, where the right-of-way cost can run $100 million in, say, the periphery of an urban area. And so this is a material. This is an ASCR cable. It has a steel core and then aluminum conductors on the outside. We use that as a baseline. This particular one is 795 circular mils of conductor. And this is basically how much current you can put through it before it gets up to a 75-degree centigrade temperature rise. The rated temperature on this is 100 degrees centigrade. So there are some alternative materials that use a composite core, either a aluminum oxide core or a carbon composite core, that reduce the sag a lot, and they can run to almost 200 degrees centigrade. So they have actually the similar conductivity, so they're still dissipative, and they can go to this particular level here. So what I took a couple of test cases. One is where I assume we just only got the conductivity of copper, and also assumed we could go to a 300 degree centigrade operating point. And this is where we had 2.5 times the conductivity of copper. This is a slightly bigger diameter. This actually matches the mass per unit length of this ASCR cable. So you can see here that you can actually push tremendously more current up at the maximum operating temperature. And even if you stuck with the same similar operating temperatures, then you can get significantly more current through this kind of a conductor. And if we actually were to achieve the 10x conductivity, it would be almost off scale. So this is a pretty appealing goal to work for, and that's one of our key projects. This is a slide that I borrowed from Rick that obviously came from St. Louis. And so, why is this? As we've learned in this conference, and it's become pretty obvious, a lot of the future power production is going to have to be, or probably will be, remote from where your major population centers are. And whether it's solar farms here or wind farms up here or big thermal hydro power projects in the Northwest or somewhere down here on the equator where they're with Rectenna farms, you're going to have to get that power to other places in the world. And so this it turns out that coming up with next generation grid technology may be enabling for that to work out. And let me see. I think I hit all the points there. So I'm done with this, and thank you very much.
Questions for Howard? Don't go away, Howard.
Okay.
Go ahead.
Yes, sir.
Excuse me.
My question regarding that after you cut the nanotube and attach the new catalyst,
Yeah.
so two questions. First, you are considering diffusion, growing nucleation, diffusion through surface or through into the catalyst, bulk diffusion or surface diffusion. And second, why, when you already attach the new catalyst, why is not going to happen nucleation of new nanotube? Why it has to go exactly to continue grow the old one?
Interesting. I didn't actually quite understand the first part of your question, but why would it not renucleate? Our intent is to operate the amplifier at a lower temperature than a typical reactor. It turns out that there are two temperature regimes. We typically are growing at about 950 degrees centigrade right now. That's a temperature at which you can nucleate new tubes, at least by this particular process. At lower temperatures, you would not be nucleating new tubes.
What hydrocarbon in that case you are using?
That's carbon monoxide in this particular case. We believe we may be also able to switch to alcohols or other feedstocks as well.
In that case, exothermic reaction, so the local temperature can be higher, and still you will have, like, you are growing the new nanotube.
Well, actually, we know that once the tube gets going, it's very, very unusual for there to be any change of the chirality of the tube, and there's very few defects, because once the tube gets nucleated, it appears to be quite stable. You can grow for actually centimeters without having any defects in the tube. So we believe, with I think a high degree of confidence, that if you have an intimately contact, and that's what the reductive docking step is for, is to make sure that the catalyst particle is intimately docked to the geometric seed, that it should then turn around and grow the same type of material perfectly.
Other questions? I have one. Two-part. Number one, what limits the length of the tube when it's grown? And number two, your spun fibers, the tubes ought to be overlapped at least by 100 nanometers. Is it simply misalignment that gives you the problems right now?
What limits the length of the tubes? If you keep the tubes separated as individuals, the length of the tube, and this is some work done by one of our collaborators, Jay Liu, seems to be limited only by the size of the substrate you can observe it on or grow it in, where he's seen 4-centimeter nanotubes. Now, that's where the tube is isolated and growing all by itself. In a higher production reactor, the tubes tend to run into each other, and they actually have huge van der Waals bundling forces. And so then the tubes on the inside will get starved for their feedstock material. That ends up limiting the growth. What was the second part of your question?
The spun fiber and misalignment of tubes, or why the low conductivity?
Well, when the tubes come out of the reactor, you can see that fluffy material. It turns out on the microscale it's very tangled up, and we have to get those things separated out and straightened. It turns out that even in oleum or functionalized nanotubes are not truly soluble in solvents, so there's still some association into domains within the oleum dope. And so one of our key goals is to improve the processing by which these almost liquid crystal-like domains will align and then coalesce into larger domains. Okay? So right now these things are getting lined up in our extruder, but they're not fully aligned with each other and they're not coalescing perfectly. So now there are very narrow linkages between these domains. We think that those bundles or those super ropes actually have very good properties, but on a macro scale we're struggling against the connectivity from one domain to the next.
Good questions? Yeah, go ahead.
First thing is finding out the metallic nature of the tube is a little tough, right? And to make sure that once you have a metallic tube that you can attach your FEMOC and make it longer and grow longer and make a fiber out of it, is it possible that during that process you may introduce some defects in that fiber that can change the metallic properties? How are you going to monitor all this? It's not as easy as semiconducting tubes, because there's the metallic. First of all, finding out the metallic part metallic part of the nanotube is difficult. You know that the material that is being passed around, 1/3 of it is metallic tubes. We have no real way of detecting them.
Well, that is a project we have to undertake. There have been some progress in that area so far. First is with certain types of laser ablation, you can produce probably 70% armchair metallic tubes.
I should know that. But
the second is that there is Jim Tour recently shown, along with I think Mike Strano, you can do selective functionalization on metallic tubes, and that's been advanced recently to the point where I think you can get 90% purity on metallics versus semiconductors, or semiconductors versus metallics. We also expect that once we get the amplifier process working, that very likely certain types of tubes will have higher growth rates than others. For instance, zigzags may grow faster than the armchairs or something. So there will probably be some selectivity that will allow us to get down to a particular type of tube that we're working with uniquely. As to the perfection over long tubes, I actually don't know what the defect density is, but there have been cases where you study for many microns and never find a defect looking at the fluorescence of individual tubes. So we think that defect density is really quite low.
But my question is, when you're trying to process and make a fiber out of it, you have to put it through oleum and dry it and so on. So you have not only mechanical and other types of stresses that can change your metallic nature of the tube.
Well, it can change the electronic structure. I thought you were talking about changing the actual geometric arrangement. Well, actually, if you anneal the tubes to over 400 degrees, well, you can anneal them in hydrogen to over 450 or 800 degrees centigrade. You get back to pristine tubes. I don't think it's going to have great properties just exactly as it's spun and then dried, coagulated and dried out of the oleum. It will have to have some very significant annealing steps afterwards to improve its crystallinity and clean up the surface.
Nate?
Yeah, I just had two quick questions. One is, you said the tubes would grow amazingly for as long as the substrate. Are there methods by which you can seed some tubes on a substrate and pull the substrate out of the growth zone, like extruding fiber of nylon and just keep growing for as long as you're willing to pull?
Well, one of our other projects is attempting to do that. We're not quite that far along, but we do have a project we called Continued Growth, where we actually we've taken one of these fibers like this and cleaved it off.
Exactly, use that as the seed.
And then that is the seed that you can put back on a couple of monolayers of metal and then start to grow from there. Yeah. At this point, there is a struggle with that in that the cleavage is not very perfect, and so we have basically a very rough surface, and you get probably a few percent nucleation. So I'm sorry I don't have a slide of that in here. I can easily get you one. Where the tubes then do grow, it looks like they're growing out tens of microns, but then they collapse, and you get floppy, and you end up with something that looks like ponytails laying around on the top of the surface. So we now are struggling to flatten out that surface and improve the nucleation density there.
Okay, that's fine.
And if that works, then that'd be great.
Exactly.
Last one.
Any special method you have for protecting the catalyst from poisoning second time when you attach new catalyst? So during the growing long one, catalyst again can be poisoned as the first time. So what's the difference between first and second step?
Well, I don't think we've observed poisoning the catalyst because in our current...
Okay, let's to say terminated all the growing. Let's to say that way.
Well, they do stop growing eventually, but it has more to do in our current system in the fact that many tubes are nucleated spontaneously in the gas phase, and then they clump together to form bundles. And then as the outer tubes land, then they starve the interior material from its growth material. So that's the termination mechanism that we see now. In the continued growth process, that would hopefully be avoided. So we're not observing any chemical poisoning, but it's more of a physical limitation, blocking from its feedstock.
Okay, let's thank Howard. Thank you. This closes the session, and Wade has some comments or an intro to, I guess, to Rick.
I think what we wanted to do is open it up for broad general discussion. If you have any unanswered questions that you wanted to ask any of our speakers, this is a last good chance to do it in person. And what we want to do is proceed to the next steps, and I think Rick could describe his viewpoint as to what those might be, and we'll also endeavor to have, within 2 weeks, I think is a promise, right, Amy, to produce a DVD. It'll actually be a set of DVDs, probably about 4 of them, that will contain the entire videotape of the meeting. So if you're puzzled by a presentation or want to think about it a little further, you'll be able to watch it again, and you'll also have a copy of the slides. And it sounds kind of silly, but you get a lot more out of it the second time, and the third time, fourth time, fifth time. Ultimately, we'll also prepare a 2-level report, a digest that will be probably an executive summary level with where we're going next, as well as a more detailed discussion, including all the pertinent answers and questions. So, Rick, you want to use that mic?
Well, I think this has been a stunningly impressive conference. I want to thank Wade and Amy Jaffe again for pulling another one of these things off. I was hoping this would not be so interesting I could actually steal away, but I had to hear every talk. I think the answer to the question, can photovoltaics and photothermal be scaled up during our lifetime to the terawatt level, is yes. And I think that I'm actually surprised that I feel content to say that now, based on what we've seen today and yesterday. This is, I think, going to end up being a very special time, both because of the presidential election being resolved and because of what's happening with worldwide fossil fuels. So that it really sets the stage well for there to be a receptive audience to posing this question and considering the answer of what can solar do? What have 30 years of funding of solar research accomplished? And it's actually pretty amazing. And I think if we put that together with a cogent argument about the likelihood of success in working on the electrical grid in 2 key areas, both long-distance transport of energy and in local, and storage, but primarily local storage, that the case then for massive renewables from solar to solve the world's energy problems gets to be really quite strong. Last night, Nate Lewis and I were sitting at dinner together and talking, and I was starting to ask him some questions about nuclear fission, because I'm looking into that. And I told him that this last year I'd been teaching a course in issues in energy, and I have a group of 20 undergraduates, and when they come in I divide them into 5 groups of 4, and I get each of them to pick a topic in energy and pursue it. And the first time I taught this course I couldn't get anybody to pick nuclear power. They just refused. Last year I got one group to pick it, and they did a good job. And to celebrate at the end of the school year, we had a little yellow school bus come up outside, and about 7 o'clock on Saturday morning, and we got in the school bus and drove down to the South Texas Nuclear Project, which is down here about almost 100 miles south of here by Matagorda Bay, and spent the day grilling the operators about the nuances of nuclear power, in particular about nuclear waste disposal and so forth. And as I was explaining this to Nate, I was telling him about how you drive up to this facility, and it's really a nature preserve. You know, it's a huge facility, but you can hardly even see the nuclear power plant for all the swamps and trees and alligators and so forth. And before I even started to tell my story about what we found in the plant, Ned said, well, consider what would happen if you just took all that acreage and covered it with photovoltaics, and how much power would generate compared to the power that's actually generated on that site. And I think that actually that's a great test case. Because I suspect the answer is that there's a similar level of power that could be, and we don't have any nuclear plants scheduled to be built in this country right now. There's a big push, and I'm actually in favor of it, that we would actually build another generation of these with technologies we have in place. Maybe as many as 100 new nuclear plants. So you get 100 gigawatts of power from that. Well, even if we decide to do that today, it would be like 2015 or so before we'd have them there, 100 gigawatts of power. Well, by 2020, 100 gigawatts of power from photovoltaics doesn't seem very reasonable. So I'm suggesting Nate's going to have probably a very important workshop that he's going to hold for DOE, probably in March, February, and with the report coming out. I'm suggesting in one of the early pages of the report there should be a little bit of artwork, which is a 1 gigawatt nuclear plant and the same real estate with solar, and let's just compare those two things. Of course, what the nuclear plant has is it can do it 24 hours a day when the wind is blowing and the sun is behind clouds. Solar can't do that, and everybody knows that. So we've got to solve the storage problem, and we've got to solve the transmission problem so we can harvest the energy from the vast deserts around the planet. In many cases, probably with the same technology that we can slather on the sides of buildings and so forth. And just from these last 2 days, I'm very optimistic that can happen during our lifetime. And that story I didn't understand it before 2 days ago, and it's certainly not well understood in the places that matter. So I urge you, if you haven't already, sign this form that will release to us the ability to put out the DVD of the full video as well as your PowerPoint, because that we can do pretty quickly, and then we can shop that around. And also, I think once we've all had a chance to look at it multiple times, we can sit down and think about whether we ought to come up with some document jointly or in some fashion to make this point about the great promise of solar energy. In any event, thank you for your attendance. This has been really terrific.
Offer any more discussion? Are there comments from the group? Comments or questions, or everybody just tired and ready to hit the road?
Well, I guess that I'll say that if it's 1 gigawatt, it's probably, if it's the same kilowatt hours as 1 gigawatt, it would be about 10 kilometers by 10 kilometers. I don't know how big your nuclear power plant is.
It might not have been that big, but it's an interesting little test.
Yeah, that's with kilowatt hours. That's not gigawatt peak. So that includes the 4 times over.
Well, at this site down here, it's actually one of the bigger nuclear sites. There's 2 1.3 gigawatt reactors running with excellent duty cycle and duty factor and excellent performance.
But the real remark I want to make is some kind of a joint statement about the synergies of the long-distance transmission and storage and solar. It would be very welcome. I think it would really be a real step forward in the policy arena, and I hope that we do come to that. I think that could be almost revolutionary.
Good.
I think this group collectively could make that, and it puts us a bit more independent from the DOE, from the energy industry, from academia, because it's a collection of all of them. So it might be more powerful. Question here? Tex.
For the solar thermal systems, storage isn't really so much an issue.
Right.
I showed an example of the power tower that was done several years ago. It could operate 24 hours a day. But the issue is really critical for concentrating the solar power is transmission.
Right.
If you can take the power from the southwest where you have an awful lot of sun and move it to the population centers, you would do a great service to this country.
Yeah. Transmission is also, I think, critical to the acceptance of nuclear power. If you could put the nuclear power reactor someplace very far away.
It would help almost everybody.
Yeah, right.
Amy?
Yeah, I think the point on that, because the science community tends to get divided in terms of getting funding, is even the carbon sequestration group, who are notably not at this meeting, and see themselves as a competing industry with political connections to states that have coal and so forth, they're not going to be able to make their technology work without long-distance transmissions either, right? Because coal seams don't happen to be located next to New York City, and geologic storage is going to have to come in from offshore. So, in the end, even if some of these carbon sequestration technologies work, they're going to need the same set of sourcing. And so, really, in terms of just convincing, I think, the policy community that investment in certain things is you have these sort of parallel investments that could be made with solar and with the electricity grid, that really the technology could really be married together with these other prongs that they're already trying. And they're actually, in my opinion, missing sort of a critical piece, because the carbon sequestration technology is useless for the same reasons we could put up the map. The carbon guys put up the map of where the geologic seams are. If they're going to get the seams to work, they're going to have to run the electricity from there, because those combined cycle coal plants are going to have to be where you're going to sequester, right? And, same as Rick's saying with the nuclear storage, if we're going to realize we can't really move it to Yucca Mountain and we're going to have to store it at the site, then the site needs to be someplace that's not 2 minutes from a city. And in almost everywhere you look, I mean, the same thing with stranded natural gas. Stranded natural gas becomes much more commercial if you could have a power station right at the gas and you're going to run the wire. So it solves a tremendous amount of issues to be able to look at it more comprehensively in that way, and a more systematic way that way. And then, of course, even the hydrogen community believes that they're going to make the hydrogen someday from renewables. So, you can really package everything together instead of just standing solar back by itself. I think there's a lot of power in combining it with some of these other things so that you're not going against the stream of what people have already tried to do, but you're joining the stream of what people have already tried to do.
I'd like to reinforce that to the point that everybody who comes back to Washington has the answer to the world's problems. And if people come back with conflicting stories that says, mine is the best, this guy over here doesn't know what he's talking about, eventually they all cancel each other out. So, indeed, if you could get a consortium of people that said, okay, here is the answer, here's the long-term goals, here's what we got to do to solve these important problems, so it's clear to the politicians that, it's not just one person waving a flag, you have a lot better chance of moving this thing forward.
Right, and so it's with that idea that we have in mind that the next workshop would be about the grid and about the issue of long-distance power transmission to enable remote sources to sell to customers thousands of miles away cheaply, and about storage technologies. And I'm a particular fan of local storage technologies at small scale, having a major research program to find ways to store 100 kilowatt hours in something not much bigger than the size of this lectern, so that you could buffer night to day in the needs of a house or a small business. If you could really do that, then you would have a huge market. You would have 100 million units in the U.S. Alone, and about 1 billion units around the world. And how about that for a new automobile industry? Being small, every time somebody makes a big technological leap, and these things can be smaller and cleaner and cheaper, then you take this one, you kick it out the back of your house, and you buy the new one. You change it every 4 or 5 years. So technological innovation gets to keep on optimizing the best possible answer to this most critical aspect on the grid. If you get to the point that most customers have that, then a lot of your peaking power generation needs go away. You have a tremendously robust electrical grid. And most critically from my viewpoint is that it now enables vast renewables, because the storage is by definition there. And so even though the cheapest power may be coming in at a time you don't need it, You can pull it into your house during the 6 hours when it's cheap and there, and use it for the rest of the time. And you will make your own decision whether or not you want 24 hours or 48 hours or 6 hours. And because it's small, you can keep on responding to new technologies. And my presumption and belief is that there must be many more technologies possible with the laws of physics and chemistry the way they are that will fit within this box at the level of 100 kilowatt hours than there are at the level of billions of kilowatt hours for, a typical power plant. There's pumped hydro, there's compressed gas. There aren't too many ways after you get past that. But inside this box, I'll bet you there are a lot. A lot of them will be driving for super batteries, for finally getting something better than lead acid battery. And through nanotechnology, bucky tubes and various things, I think we have a reasonable chance of doing it. That's a tremendously fertile area to push because it's very possible that in the effort to do that with a fixed facility in a house, you may find innovations that will work also in automobiles. And we can start getting at the mobile thing. So I think it's a very fertile thing. And the nice aspect of talking about the grid is, as we were saying, everybody gets to play. All power generation lobbies could find something about that they liked. But for solar, and massive solar, I think it's absolutely critical. Close it up, please.
Okay, well, I'd like to thank Amy for hosting us here at the Baker Center. Her incredible staff here, from Jolene Connors, who's not here at the moment, I guess, but working upstairs on the report already, right? And our AV people, hardworking 2 days, and great job. Carlos Garcia, my assistant, was a trooper also. Anybody else? Who am I missing? and his excellent choice of restaurants, I think, too. So we will also send out a little survey sheet that will ask your opinions about several things. For example, it seems that a Saturday-Sunday workshop is about the only time we can get a lot of very important people who are very busy together, and that forces people to give up a weekend, but hopefully the benefit and the outcome will be worth the sacrifice. If we plan far enough ahead, we might be able to do an actual weekday workshop, which is a little more humane. And that would bring up the question of when we might do the next workshop. And on one hand, we'd like to hurry and do this soon, like maybe next May. And if we scheduled it now and found a week or two to pulse everyone here, and also the people that need to come for a grid workshop that aren't here, we'll shoot for a weekday workshop, I would hope. If we push it off until next October, then we ought to really be able to do that, I would think. We'd also like your suggestions on who ought to come to a workshop that is focused on the grid and perhaps storage as a secondary question, and whether we could do a full workshop in 2 days or 3 days. So we'll put some questions out. I know there are a few people that we would have liked to have had here with this group, but I think we certainly had well above a critical mass for some great discussion and to get into just about all the issues that we were aware of beforehand that ought to be discussed, and I think we've got through those pretty well. So with that, at the stroke of 3:10, I declare the workshop over, and thank you for your attendance.